Welcome to the first lecture on the course on programming data structures and algorithms in Python. Let's start with the basic definition of what we mean by an algorithm and what programming is. As most of you probably know, an algorithm is a description of how to systematically perform some task. So an algorithm consists of a sequence of steps which we can think of as a recipe in order to achieve something. So the word recipe, of course, comes from cooking, where we have a list of ingredients and then a sequence of steps to prepare a dish. So in the same way, an algorithm is a way to prepare something or to achieve a given task. So in the context of our thing, a recipe is what we call a program. And we write down a program using a programming language. So the goal of a programming language is to be able to describe the sequence of steps that are required and to also describe how we might pursue different sequences of steps if different things happen in between. So the notion of a step is something that can be performed by whatever is executing the algorithm. Now a program need not be executed by a machine, although that will be the typical context of computer programming, where we expect a computer to execute our steps. A program could also be executed by a person. For instance, supposing the task at hand is to prepare a hall for a function. So this will consist of different steps, such as cleaning the room, preparing the stage, making sure the decorations are up, arranging the chairs, and so on. This will be executed by a team of people. Now, depending on the expertise and the experience of this group of people, you can describe this algorithm at different levels of detail. For instance, an instruction such as arrange the chairs would make sense if the people involved know exactly what is expected. On the other hand, if this is a new group of people who have never done this before, you might need to describe the step in more detail. For instance, you might want to say that arrange the chairs in 8 rows and put 10 chairs in each row. So the notion of a step is subjective. It depends on what we expect of the person or the machine which is executing the algorithm. And in terms of that capability, we describe the algorithm itself. Our focus in this course is going to be on computer algorithms. And typically these algorithms manipulate information. The most basic kind of algorithm that all of us are familiar with from high school is an algorithm that computes numerical functions. For instance, we could have an algorithm which takes two numbers x and y and computes x to the power y. So we have seen any number of such functions in school, for example, to compute square root of x. So what we do in school is we have a complicated way to compute square root of x, or we might have x divided by y where we do this long division and so on. Right? So these are all algorithms which compute values given one or more numbers. They compute the output of this function. But all of us who have used computers know that many other things also fall within the realm of computation. For instance, if we use a spreadsheet to arrange information and then we want to sort a column. So this involves rearranging the items in the column in some order, either an ascending order or a descending order. So reorganizing information is also a computational task, and we need to know how to do this algorithmically. We also see computations around us in our day-to-day lives. For instance, when we go to a travel booking site and we try to book a flight from one city to another city, it will offer to arrange the flights in terms of the minimum time or the minimum cost. So these are optimization problems. This involves also arranging information in a particular way and then computing some quantity that we desire. In this case, we want to know A, that we can get from A to B, and B, among all the different ways we can get from A to B, we want the optimum one. And of course, there are very, very many more things that we see day to day which are executed by computer programs. We can play games. For instance, we can solve Sudoku, or we can play chess against a program. When we use a word processor to type a document, or even when we use our cell phones to type SMS messages, the computer suggests corrections in our spelling. Okay? So we will look at some of these things in this course, but the point is to note that a program in our context is anything that looks at information and manipulates it to a given requirement. So it's not only a question of taking a number in and putting a number out. It could involve rearranging things. It could involve computing more complicated things. It could involve organizing the information in a particular way so these computations become more tractable, and that is what we call a data structure. So to illustrate this, let us look at a function which most of us have seen and try to understand it algorithmically. So the property that I want to compute is the greatest common divisor of two positive integers m and n. So as we know, a divisor is a number that divides. So k is a divisor of m if I can divide m by k and get no remainder. So the greatest common divisor of m and n must be something which is a common divisor. So common means it must divide both. Okay, and it must be the largest of these. So the largest k such that k divides m and k also divides m. For instance, if we look at the numbers 8 and 12, then we can see that 4 is a factor of 8, 4 is a divisor of 8, 4 is also a divisor of 12. Another divisor of 12 is 6, but 6 is not a divisor of 8. So if we go through the divisors of 8 and 12, it's easy to check that the largest number that divides both 8 and 12 is 4. So GCD of 8 and 12 is 4. What about 18 and 25? 25 is 5 by 5, so it has only one divisor other than 1 and 25, which is 5, and 5 is not a divisor of 18. But fortunately, 1 is a divisor of 18, so we can say that GCD of 18 and 25 is 1. There is no number bigger than 1 that divides both 18 and 25. Since 1 divides every number, as we saw in the case of 18 and 25, there will always be at least one common divisor among the two numbers. So the GCD will always be well defined. It will never be that we cannot find a common divisor. And because all the common divisors will be numbers, we can arrange them from smallest to largest and pick the largest one as the greatest common divisor. So given any pair of positive numbers m and n, we can definitely compute the GCD of these two numbers. So how would one go about computing GCD of m and n? So this is where we come to the algorithmic bit. We want to describe a uniform way of systematically computing GCD of m and n for any m and any n. So here is a very simple procedure. It's not the most efficient. We will see better ones as we go along. But if we just look at the definition of GCD, it says, look at all the factors of m, look at all the factors of n, and find the largest one, which is a factor of both. So the naive way to do this would be to first list out all the factors of the first number m, then list out all the factors of the second number n, and then among these two lists, report the largest number that appears in both lists. This is almost literally the definition of GCD. Now, the question is, does this constitute an algorithm? Well, at a high level of detail, if we think of list out factors as a single step, what we want from an algorithm are two things. One is that the description of what to do must be written down in a finite way. In the sense that I should be able to write down the instructions regardless of the values of m and n in such a way that you can read it and comprehend it once and for all. So here it's very clear we have exactly 3 steps, right? So we have 3 steps that constitute the algorithm. So it's certainly presented in a finite way. The other requirement of an algorithm is that we must get the answer after a finite number of steps. Now this finite number of steps may be different for different values of m and n. You can imagine that if you have a very small number for m, there are not many factors. If you have a very large number for m, you might have many factors. So the process of listing out the factors of m and n may take a long time. However, we want to be guaranteed that this process will always end, and then having done this, we will always be able to find the largest number that appears in both lists. So to argue that this process is well defined, all we need to realize is that the factors of m must be between 1 and m. In other words, although there are infinitely many different possibilities as factors, we don't have to look at any number bigger than m because it cannot go into m evenly. So all we need to do to compute the factors of m is to test every number in the range 1 to m. And if it divides m without a remainder, then we add it to the list of factors. So we start with an empty list of factors and we consider in turn 1, 2, 3, 4 up to m. And for each such number, we check whether if we divide m by this number, we get a remainder of 0. If we get a remainder of 0, we add it to the list. So let us look at a concrete example. Let us try to compute the GCD of 14 and 63. So the first step in our algorithm says to compute the factors of 14. So by our observation above, the factors of 14 must lie between 1 and 14. Nothing bigger than 14 can be a factor. So we start by listing out all the possible factors between 1 and 14 and testing them. Right? So we know, of course, that 1 will always divide. In this case, 2 divides 14 because 14 divided by 2 is 7 with no remainder. Now 3 does not divide, 4 does not divide, 5 does not divide, 6 does not divide, but 7 does, because if we divide 14 by 7, we get a remainder of 0. Then again 8 does not divide, 9 does not divide, and so on. And finally we find that the only other factor left is 14 itself. Right? So for every number m, 1 and m will be factors, and then there may be factors in between. So having done this, we have now identified the factors of 14, and these factors are precisely 1, 2, 7, and 14. So the next step in computing the GCD of 14 and 63 is to compute the factors of 63. So in the same way, we write down all the numbers from 1 to 63 and we check which ones divide. So again, we'll find that 1 divides. Here 2 does not divide because 63 is not even. 3 does divide. Okay, then we'll find a bunch of numbers here which don't divide. And then we'll find that 7 divides because 7 nines are 63. Then again 8 does not divide, but 9 does. Then again there are a large gap of numbers which don't divide. And then 21 does divide because 21 threes are 63. And then finally we find that the last factor that we have is 63. So if we go through this systematically from 1 to 63, crossing out each number which is not a factor, we end up with the list 1, 3, 7, 9, 21 and 63. Having computed the factors of the two numbers 14 and 63, the next step in our algorithm says that we must find the largest factor that appears in both lists. So how do we do this? How do we construct a list of common factors? Now there are more clever ways to do this, but here is a very simple way. We just go through one of the lists, say the list of factors of 14, and for each item in the list, we check if it is a factor of 63. Right? So we start with 1 and we say, does 1 appear as a factor of 63? It does, so we add it to the list of common factors. Then we look at 2 and then we ask, does it appear? It does not appear, so we skip it. Right? Then we look at 3 and look at 7 rather, and we find that 7 does appear, so we add 7. Then finally we look at 14 and find that 14 does not appear, so we skip it. So in this way, we have systematically gone through 1, 2, 7 and 14 and concluded that of these only 1 and 7 appear in both lists. And now having done this, we have a list of all the common factors. We computed them from smallest to biggest because we went through the factors of 14 in ascending order. So this list will also be in ascending order. So returning the largest factor just returns the rightmost factor in this list, namely 7. So this is the output of our function. So we have computed the factors of 14, computed the factors of 63, systematically checked for every factor of 14 whether it's also a factor of 63 and computed this list of common factors here. And then from this list, we have extracted the largest one, and this in fact is our GCD. Okay? So this is an example of how this algorithm would execute. So if we were to write it down in a little more detail, then we could say that we need to notice that we need to remember these lists, right, and then come back to them. So we need to compute the factors of 14, keep it aside, we need to write it down somewhere. We need to compute the factors of 63, write it down somewhere, and then compare these two lists. So in other words, we need to assign some names to store these. So let us call fm for factors of m and fn for factors of n as the names of these lists. So what we do is that we run through the numbers 1 to m, And for each I in this list 1 to m, we check whether I divides m, whether m divided by I has remainder 0, and if so, we add it to the list factors of m or fn. Similarly, for each j from 1 to n, we check whether j divides n, and if so, we add it to the list fn. Now we have two lists, fm and fn, which are the factors of m and the factors of n. Now we want to compute the list of common factors, which we will call CF. So what we do is, for every f that is a factor of the first number, remember in our case it was 14, for each f, so we ran through 1, 2, 7 and 14 in our case, right? So for each f in this list, we add f to the list of common factors if it also appears in the other list. So in the other list, if you remember, it was 1, 3, 7, 9, 21 and 63. So we compare f with this list, and if we find it, we add it to CF. And having done this, now we want to return the largest value in this list of common factors. Remember that 1 will always be a common factor, so the list CF will not be empty. So there will be at least one value. But since we add them in ascending order, since the list fm and fn were constructed from 1 to m and 1 to n, the largest value will also be the rightmost value. So this gives us a slightly more detailed algorithm for GCD. It's more or less the same as the previous one, except it spells out in a little more detail how to compute the list of factors of m, how to compute the list of factors of n, and how to compute the largest common factor between these two lists. So earlier we had 3 abstract statements. Now we have expanded it out into 6 slightly more detailed statements. So this already gives us enough information to write our first Python program. Of course, we will need to learn a little more before we know how to write it, but we can certainly figure out how to read it. So what this Python program is doing is exactly what we described informally in the previous step. So the first thing in the Python program is a line which defines the function. So we are defining a function GCD of m comma n. So m and n are the two arguments which could be any number, like any function. It's like when you write f of x, y in mathematics, it means x and y are arbitrary values, and for every x and y you do something depending on the values that you call the function with. So this says that this is a definition, so def for definition, of a function GCD mn. So now the first step is to compute the list of factors of m. In Python, we write a list using square brackets. So a list is written as x, y, z and so on. So the empty list is just an open bracket and a square close bracket. So we start off with an empty list of factors. So this equality means assign a value. So we assign fm, the list of factors of m, to be the empty list. Now we need to test every value in the range 1 to n. Now Python has a built-in function called range, but because of, we shall see, because of a peculiarity of Python, this returns not the range you expect, but one less. So if I say give me the numbers in the range 1 to n plus 1, it gives me numbers in the range 1 to m, 1 up to the upper limit but not including the upper limit. So this will say that I takes the values 1, 2, 3 up to m. For each of these values of I, we check whether this is true. Now percentage is the remainder operation. So it checks whether the remainder of m divided by I is 0. If the remainder of m divided by I is 0, then we will append I to the list fn. We will add it to the right. Okay, append is the English word which just means add to the end of the list. So we append I to m. So in this step, we have computed fm. This is exactly what we wrote informally in the previous example. Right? We just said that for each I from 1 to m, add I to fm if I divides n. And now we have done it in Python syntax. So we have defined an empty list of factors, and for each number in that range, we have checked if it is a divisor and then added it. And now here we do exactly the same thing for n. Right? So we start with the empty list of factors of n. For every j in this range, if it divides, we append it. And now at this point, we have two lists, fm and fn. And now we want to compute the list of common factors. So we use CF to denote the list of common factors. Initially, there are no common factors. Now, for every factor in the first list, if the factor appears in the second list, then we append it to CF. Right? So the same function append is being used throughout. It says take a list and add a value. Which value? We add the value that we are looking at now, provided it satisfies the condition. So earlier we were adding it provided the divisor was 0, the remainder was 0. Now we are adding it provided it appears in both lists. For every f in the first list, if it appears in the second list, add it. So after this, we have computed fn, CF. And now we want the rightmost element. So this is just some Python syntax which you'll see, which says that instead of, if you start counting from the left, then the numbers, the positions in the list are numbered 0, 1, 2, 3, 4. But Python has a shortcut which says if you want to count from the right, then we count the numbers as -1, -2, and so on. So it says return the -1th element of CF, which in Python jargon means return the rightmost element. So this is the rightmost element. So at this point, it's enough to understand that we can actually try and decode this code, this program, even though we may not understand exactly why we are using colons in some places and why we are pushing some things. See, notice that there are other syntactic things here. So there are, for example, you have these punctuation marks which are a bit odd, like these colons. Then you have the fact that this line is indented with respect to this line, and this line is indented with respect to this line. So these are all features that make Python programs a little easier to read and write than programs in other languages. So we will come to these when we learn Python syntax more formally, but at this point you should be able to convince yourself that this set of Python steps is a very faithful rendering of the informal algorithm that we wrote in the previous slide. So let's note some points that we can already deduce from this particular example. So the first important point is that we need a way to keep track of intermediate values. So we have two names to begin with, the names of our arguments m and n. Then we use these three names to compute these lists of factors and common factors. And we use other names like I, j, and f in order to run through these. We need I to run from 1 to m. We need j to run from 1 to n. Of course, we could reuse I, but it's okay. We use f to run through all the factors in CF. So these are all ways of keeping track of intermediate values. The second point to note is that a value can be a single item. For example, m, n are numbers. Similarly, I, j, and f at each step are numbers. So these could be single values, or they could be collections. So there are lists. Right? So fm is a list, fn is a list. So it's a single name denoting a collection of values, in this case a list, a sequence. It has a first position, a next position, and a last position. Okay? So these are lists of numbers. One can imagine other collections, and we will see them as we go along. So collections are important because it would be very difficult to write a program if we had to keep producing a name for every factor of m separately. We need a name collectively for all the factors of m regardless of how big m is. Okay? So these names can denote single values or collections of values. And a collection of values with a particular structure is precisely what we call a data structure. Right? So these are more generally called data structures. So in this case, the data structure that we have is a list. So what can we do with these names and values? Well, one thing is we can assign a value to a name. So for instance, when we write fn is equal to the empty list, we are explicitly setting the value of fn to be the empty list. Right? This tells two things. It says the value is an empty list. It also tells Python that fn denotes a list. So there are two steps going on here, as we will see. And the other part is that when we write something like for each f in the list CF, this is implicitly saying that take every value in CF and assign it one by one to the value f, to the name f. Right? So though we don't have this equality sign explicitly, implicitly this is assigning a new value for f as we step through the list CF. Right? So the main thing that we do in a Python program is to assign values to names. And having assigned a value, we can then modify the value. For instance, every time we find a new factor of n, we don't want to throw away the old factor. We want to take the existing list fn and we want to add it. So this function append, for instance, modifies the value of the name fn to a new name which takes the old name and sticks an I at the end of it. Right? So more generally, we could have a number and we could want to replace it by 2 times the number. So we might have something like I is equal to 2 times I. So star stands for multiplication. This does not mean that I is equal to 2 times I arithmetically, because obviously unless I is 0, I cannot be equal to 2 times itself. What this means is take the current value of I, multiply it by 2 and assign it to I. So we will see this as we go along. But assignment can either assign a completely new value or it could update the value using the old value. So here we are taking the old value of the function of the list fn and we are appending a value to it and getting a new value of fn. The other part that we need to note is how we execute steps. So as we said at the beginning of today's lecture, a program is a sequence of steps, but we don't just execute a sequence of steps from beginning to end blindly. Sometimes we have to do the same thing again and again. For instance, we have to check for every possible factor from 1 to m if it divides m and then put it in the list. Right? So some steps are repeated. We do something, for example, here for each item in a list. And some steps are executed only if the value that we're looking at meets a particular condition. Right? So when we say something like if m% I is 0, if the remainder of m divided by I is 0, then append. Okay, so the step append I to fm, the factors of m. This happens only if I matches the condition that it's a factor of m. So we have repeated steps, the same thing done again and again, and we have conditional steps, something which is done only if a particular condition holds. So we'll stop here. So this example should show you that programs are not very different from what we know intuitively. It's only a question of writing them down correctly and making sure that we keep track of all the intermediate values and steps that we need as we go along so that we don't lose things. We will look at this example in more detail as we go along and try to find other ways of writing it and examine other features. But essentially, this is a good way of illustrating programming.